Alright, hello everybody. This video is going over the AP Chemistry 7.2 lesson, which is direction of reversible reactions. At the end of this lesson, you should know if the rate of the forward reaction is greater than the reverse reaction, then there is a net conversion of reactants to products. If the rate of the reverse reaction is greater than that of the forward reaction, then there is a net conversion of products to reactants. An equilibrium state is reached when these rates are equal. So first, I just want to go over irreversible versus reversible reactions. Up until this point, we have focused on irreversible reactions, which is just when you have chemical reactions that involve reactants forming products. Well, now we're going to go into reversible reactions, which are represented by this double arrow that you see on the screen. And if you want to pause this video and kind of go over this table on the right, you can see the difference between those two types of reactions. So first, let's go into what a dynamic equilibrium is. This can be defined as the steady state of a reversible reaction, which occurs in a closed system, which we already talked about in 7.1. So in a dynamic equilibrium, both the forward and reverse reactions are going to proceed in opposite directions with equal rates. And then the concentration of the reactants and products remain constant at the equilibrium. So if you look at this figure on the right here, we have two different equilibrium graphs. One is based on reaction rate and one is based on concentration. You can see that the reaction rate graph, they are going to end up being the same rate, which is why you see that they are the exact same once the equilibrium is reached. However, in concentration, it doesn't mean that the concentration is going to be exactly the same. It just means that they are going to be constant. So as you can see, once you get to this line here, the equilibriums is when the concentration remains constant. So how do we interpret these graphs? At equilibrium, the rates of the forward and backward reactions are equal. So remember, this is a dynamic equilibrium. So when we're looking at the rate graph, it should indicate that both the forward and backward rates are equal. So at T1, the rates are equal and the reaction is at equilibrium. So at T1, you can see the rates are equal and they are at equilibrium. So for concentration time graphs, which are the two graphs on the right, equilibrium is depicted when there is no change in the reactants or products. Notice how the concentrations of products and reactants do not have to be the same, whereas in the rate graph, they do have to be the same. So when looking at a concentration time graph, which is again over here on the right, we can tell when a system has reached equilibrium by the flat line of the concentration graphs. So at T1, you can see that equilibrium has been reached because those concentrations are no longer changing. They are constant. So let's just kind of sum up what we've learned so far just to make sure we're all on the same page. So we know equilibrium can be described as the settling of the rates of reversible reactions. So if we're talking about something very basic, like A forming B and B forming A, you have two reactions. You can go forward, A to B, or you can go backwards, B to A, and that forms that one full equilibrium reaction. So equilibrium is the point at which the rates of these reactions are equal, which you can see in the rate versus time graph. The amount of A created, and when you see amount, that's the same as concentration, because you will normally see concentration here and not amount. But amount of A created is equal to the amount of B created over a period of time. So the concentrations do not change once they hit equilibrium. So we can represent this graphically by showing both the rates of the reaction and the concentrations of the products and the reactants as the reaction goes forward. So let's look into product favored versus reactant favored. So there are two ways to see whether a reaction is product favored or reactant favored. One is just by looking at the equilibrium graph, or you can also do it by looking at the K value, which is the equilibrium constant. So let's start with this graph on the right here. We have sulfur dioxide and oxygen gas as our reactants, and then we have sulfur trioxide as our product. If you look at this equilibrium chart with concentration versus time, you can see that sulfur trioxide, which is our product, ends up with a much higher concentration than our two reactants. That is going to tell us that this reaction is product favored. So the reason it's product favored is because at equilibrium, the concentration of the product is larger than the concentration of the reactants. So that is one way you can find whether a reaction is product favored or reactant favored. Another way you can do that is by looking at the K value, which is the equilibrium constant. And remember, the equilibrium constant is the concentration of the products over the concentration of the reactants. So if you are given a K value that is less than 1, that reaction is going to be reactant favored. If you are given a K value that is greater than 1, that reaction is going to be product favored. And if you are given a K value that equals 1, that means you have equal proportion of reactants and products at equilibrium, which is extremely rare. So this is just a side note with catalysts that I wanted to bring up because we had a nice graph to compare to the last slide. I just want to reiterate that a catalyst has an effect on the amount of time it takes for the reactants and products to reach equilibrium, but it does not affect the concentration. So if you look at the previous slide, you can see the concentrations of the product and the two reactants are the same. It just decreased the amount of time it took for the reactants and product to reach that equilibrium state. All right, so let's look into some conceptual understanding on what we were talking about with the K values. So if we look at our first example, we have N2O4 as our reactant and NO2 as our product. It's telling us that the K value is 4.65 times 10 to the negative third. For this specific reversible reaction, the K value is less than 1, which means that the reaction is going to be reactant favored. Now, if we look at our second example, we have O3 as our reactant and O2 as our product. The K value is 2.5 times 10 to the 12th. For this reaction, it has a K value of greater than 1. That's going to mean that the reaction is product favored. The easiest way to think of this is to go back at what K means. K is generally the ratio of the products over the reactants. Therefore, if the reactants are favored in a greater quantity, the denominator of K is going to be larger than the numerator. The smaller the denominator, the smaller K is. This is one way to explain why the reaction is reactant favored when K is less than 1. So you can always kind of go back to that conceptual understanding of the equation when you have products over reactants for the equilibrium constant. Then if you look at the figure on the right, this is just a visual representation of what we just talked about. So you can see on the top part of this, when your equilibrium constant is greater than 1, you have a higher concentration at equilibrium of your products. Then when your equilibrium is less than 1, that means at equilibrium, your reactants are going to have a higher concentration. And then this is the very rare example. If your K value is equal to 1, that means you have an equal concentration of both your reactants and your products. So what does knowing the direction tell us? So by observing K, we can make qualitative judgments on how far a forward reaction goes. The higher value of K implies that from reactants, more products are created. A reaction with a lower K value will not go as far forward, producing less products. So for example, if we have two reactions and one has a K value of 1.3 times 10 to the 6th, and the other has a K value of 2.3 times 10 to the 8th, we know that both of these reactions are product favored because they're greater than 1, but which one is more product favored? So since the second reaction has a higher K value, we know that the reaction will go farther forward than the first K value, which will produce more product. All right, so let's go over an example to solidify what we've learned in this lesson. So we have two reversible reactions, one with acetic acid and one with carbonic acid. The reversible reaction with acetic acid produces a K value of 1.8 times 10 to the negative fifth, and the reversible reaction with carbonic acid has a K value of 4.3 times 10 to the negative seventh. So looking at these K values, we know that both of them are less than 1, which means we know that both of these reactions are going to be reactant favored. Now, what does reactant favored mean? It means that the reactants are going to have a higher concentration than the products will at equilibrium. So if we look at the two K values, you can see that carbonic acid has a lower K value than acetic acid does. That means it will go further forward than acetic acid will, even though both are reactant favored. Since the concentration of carbonic acid will be higher than the concentration of acetic acid, we know that acetic acid will produce more H plus ions than carbonic acid will. So since acetic acid will produce more H plus ions, we can evaluate that acetic acid is going to be a stronger acid than carbonic acid will at the same concentration. All right, I hope this video helped you. I hope you have a great day, and I will see you tomorrow.